We start in the discrete case, discrete bivariate random variable. We start with two random variables that are discrete, x and y. Discrete univariate random variables. And we create, you could call it a vector random variable, but we're going to write it with point notation, x comma y. And we say when we do this that they're going to have some sort of joint distribution. There are lots of ways we could try to create a joint distribution for x and y. Okay, there are infinitely many ways. Even though x and y might be something specific, there are infinitely many ways we could try to create some sort of joint distribution from them. So when I say this has a joint distribution, keep that in mind. How do I specify what the joint distribution is? I use a joint PDF, or in the discrete case, we could also call it a joint PMF. I will call it a joint PMF. Probability mass function. Here I am trying to be consistent with the book using subscripts. Calling it a PMF is not consistent with the book, but it's what I personally prefer to call it a probability mass function because you use it to calculate probabilities directly, just like in the discrete case in chapter 3. And it's the probability of the event that capital X equals little x and capital Y equals little y. Notice the word "and" there is very important. Now, such a joint PMF could be specified with a formula, but more commonly here at the beginning, we specify it with a table. And to keep it simple, let's keep the number of possible values where this takes on a non-zero value relatively small. Oh, I think I usually make x go across the top and y go down the bottom here, down the side. Let's say x can take on the values 0 and 1, and y can take on values 2 and 3 with non-zero probabilities. The numbers that I put in the main body of the table here, these 4 different spots, are going to represent 4 probabilities. The one up here would be the probability that capital X is 0 and capital Y is 2. The one that goes right there would be the probability that capital X is 1 and capital Y is 2. Here, where capital X is 0 and capital Y is 3. Here, where capital X is 1 and capital Y is 3. And to be a joint PMF, I hope you could guess, you don't want to put any negative numbers on the table. And what else do you think you need? Second thing, all the probabilities should add to 1. So I can create any combination of 4 numbers here that are non-negative and add to 1, and it would be a valid joint PMF. Oh, how about 0.15, I have to be, well, okay, I have to be careful. Not any. 0.85. Excuse me. I got confused. 0.4, 0.3 say, and what am I up to? I'm up to 0.85 now. I guess this needs to be a 0.15 as well. I got confused then. Right, those 4 numbers, if I've calculated in my head correctly, do add up to 1. This would be a valid joint PDF. From this, can we recover the PMFs of X and Y individually? Well, if you knew what X and Y were ahead of time, not necessarily. But if we don't know what X and Y are ahead of time, if this is essentially going to define the distributions of X and Y individually, then we can use it. How? The distribution for X can take on values of 0 and 1 are found by adding vertically. I don't remember if X typically is across the top and Y is typically across the bottom, the side. But let's do it that way anyway. The PMF for X, say little f sub capital X of X, is found by adding down these columns, if I make my table this way, because those are the two different values that x can take on. X will take on a value of 0 with probability equal to the sum of these two numbers, 0.55. And x will take on a value of 1 with the sum of these two numbers. The probability that x equals 1 would be the value of this function, 0, thank you, at 0, which is 0.55. And this 0.45 would be the probability that x, capital X equals 1. You could call that f sub x of 1 is 0.45. The PMF for y is found by adding across the rows. Again, in the book, these might be switched around with the roles of x and y. I'm not remembering. So the PMF for y is found by adding across 0.15 plus 0.3 would be 0.45, and 0.4 plus 0.15 would be 0.55. And it's accidental that these numbers end up being the same in a switched order here. That's accidental. Okay, so this would be little f sub capital Y of 2, and this would be little f sub capital Y of 3. That's the probability that capital Y equals 2, and this is the probability that capital Y equals 3. These numbers, these function values being in the margins of these tables makes us call these marginal distributions. If we only know the joint distribution, we figure out the marginal distributions this way. If we happen to know the distributions of x and y ahead of time, I would not have been able to enter what were essentially random probabilities in here, because I would need the marginal distributions to be consistent with the original distributions of x and y. So just realize that for the most part, we're starting with the joint distribution and we're going to the margin. You can write what we did here in terms of formulas. You can say the marginal distribution PMF of x is a sum of joint distribution values as y varies. I'll put all y here. In the present case, where y can only take on the values of 2 and 3 with positive probability, this is going to be f of x comma 2 plus f of x comma 3. It would be a sum y going from 2 to 3. What's x? X could be either 0 or 1. I could either evaluate this at 0, and if I do that, I'll get 0.55. Or I can evaluate this at x equals 1 and get 0.45. I'm effectively, you might say, summing out the y values, in a sense, to get something that only depends on x. The marginal distribution for y is a similar kind of sum, except you sum over all x. And since, again, for this example, f only takes on values 0 and 1 with positive probability, this is going to be f of 0 comma y plus f of 1 comma y. These last equalities being for the present example. For this example. Okay. So once again, with this one, I could use this with y equal to 2 or y equal to 3. If I plug in y equal to 2, I'm adding these two values, and I get 0.45. If I plug in y equal to 3, I'm adding these two values, and I get 0.55. That's called the marginal distribution. I think it's also worth, in this context, right away here, emphasizing the idea of independence. I'm using notation that's not completely consistent with chapter 2 right here. I'm using the word and. I'm also not using like an A and a B representing events. If you want to be real precise about what the events are, it gets complicated. So we're being a little bit hand-wavy here in terms of our notation. But effectively, if x and y, if these two events, x equaling little x and y equaling little y, are independent, then we know from the multiplication rule for independent events that this probability should be the product of two probabilities like that. This is really a definition. If and only if X and Y are independent. But wait a minute. We've talked about independent events. We haven't really talked about independent random variables. Well, that's what I'm talking about right now. This is essentially a definition in this context of a discrete random variable. Again, X and Y are still discrete here. In the context of a discrete random variable, we're saying X and Y are independent as random variables if this equality is true. In terms of their probability mass function, this is equivalent to saying that the joint PMF equals the product of the marginal PMFs for all values of little x and little y, by the way. Forgot to mention that. You want this to be true for all little x and little y. So this makes sense in terms of what we learned in chapter 2 in the context of a discrete random variable here like this, a discrete bivariate random variable. But we also use this equality to define independence even if x and y were continuous. But you can't make sense of it in terms of probability like this in that context. It's still going to be our definition of independence, even when x and y are continuous. And that'll be what we end with, is what is a continuous bivariate random variable. A continuous bivariate random variable. We start by assuming x and y are continuous. And once again, we can put them together into a vector, you might say, a bivariate random variable that is going to have a joint distribution, that it would be a continuous distribution, a continuous PDF. And once again, there are infinitely many ways this could be done to still even be consistent with the PDFs of x and y individually. But again, most typically, we don't think about their PDFs individually first. We think about the joint distribution first. The joint PDF is still going to be denoted little f sub capital XY of little xy. But now this no longer represents a probability, right? Just like in chapter 4, the PDF didn't represent a probability, represented a probability density. We have to integrate it to find probabilities. But being a multivariable function, we have to do double intervals to find probabilities. It's simplest if you are describing your probability that you're after in terms of inequalities like this. Say capital X is between A and B, and capital Y is between C and D. Effectively, geometrically, we are thinking about a rectangle of values that this joint random variable can take on. X goes from A to B, Y goes from C to D. This rectangle in the plane is a way to visualize this event effectively. These inequalities are both going to be true. This one and that list of inequalities are both going to be true if and only if this bivariate random variable takes on a value, so to speak, that is a point in this rectangle. And we find probabilities in the continuous case by integrating the PDF over this rectangle. This is often written in a couple different ways. If I call this region R, you could write the integral that you're after in an abstract way with two integral signs, because it's a double integral. Put the region down there, put the function you're integrating right there, And then, not going to worry about the meaning of this today. I'll hint at the meaning next time. Instead of writing dx dy or dy dx, you, in an abstract sense, you write dA, where dA represents what's something called an area element. It can be effectively imagined to be the area of a tiny rectangle. I don't want to say any more than that, okay? But to do this integral, hang with me here, we got 1 minute. To do this integral, you do it as a sequence of two integrals, an inner integral and an outer integral. Parentheses, like I'm putting here, are not necessary, and people don't usually put them, but conceptually, it's helpful to do something like this. The inner integral is to integrate the joint PDF with respect to y going from C to D. When you do that integral, which everybody can do, even if they haven't had multivariable calculus, your answer will depend on x, and in fact will be the marginal distribution of x. And then you integrate that function as a function of x from a to b. This is called an iterated integral. You're doing an inside integral first, and then an outside one. People don't typically put the parentheses there. You don't have to. But just realize, conceptually speaking, that it's helpful. The order, doing it with respect to y first, then with respect to x, is arbitrary. In our nice situations that we'll encounter, you could do it the other direction and get the same answer. All right, have a good day.